And we're back in the cave. Next verse, same as the first, right? Just like class, here we go again. I say pause, you pause, do the thing. After you're done with the thing, hit play, I'm here with the answers. In between, I have a 3 to 4 second awkward pause staring around my desk. Other than that, same as class, we're going to do you do, I do, you do, I do, you do, I do, and there goes our math lesson. We're going to do 2-6 today, but we started the same as any other class. Daily quiz. Get going. Okay, we're back. If I'm going to solve a rational equation, then factor, factor, friggin' factor, I see that this is m minus 4, m minus 3, very handily, those two factors. So I get common denominators by taking this times m minus 4, numerator and denominator, this by m minus 3, numerator, denominator. Now that they're all over m minus 4, m minus 3, or this quadratic, if I multiply the whole honkin' thing by that quadratic, they will womp, womp, cancel, leaving me with just my numerators, but now those two are combined. So I'll have 3m minus 12 plus 4m minus 12 is 25, combined like terms. 7m minus 24 is 25, 7m is 49, and m is 7. But because my original has a variable on denominator, I have to check for the first commandment of domain, thou shalt not divide by 0. Make sure that you actually plug it back in and check, and sure enough, this one works. So this one was very straightforward. In fact, taken straight out of Algebra 1 textbook. So this one should be a slam dunk for us. I'm going to say, did you get common denominators by multiplying by binomials instead of trying some other freshman shenanigans? Did you distribute correctly? Did you get down to the correct answer? Did you actually check it? Is that worth it? Things. I should have made one that had an extraneous solution. That's where my other point was going to be. I was too nice to you. So, freebies. We're going to say, did you go to get common denominators? Did you distribute correctly? Did you solve stuff, get down to correct answer, and then one floating for the dumb? Remember, sometimes we just make a big oof and miss a negative, something like that. So there's your out of 5. Again, when it comes to the homework, so far it's been pretty quiet on Remind. If you have questions, you have to ask, because I'm going to assume that if you're not asking questions, you know exactly what's going on, and we're all going to crush our next quiz. So, speak or forever hold your pieces. We're going to move into 2-6. Again, your notes right there. You got them right in front of you, so I'm just going to leave it as kind of a thumbnail up above my head here, and I have to do it like this because I don't have them printed off at home. We're just going to go on paper like this. So, starting with a little bit of explanation talk. Nonlinear inequalities. See, if I asked where this function was greater than 0, less than 0, greater than, or less than or equal to, greater than or equal to 0, if I had instead of equals 0, well, when I ask equals 0, then, it's a polynomial. We do all of our stuff like rational root theorem, Descartes' law of signs, use our upper and lower boundary test to kind of narrow down our options, or we just guess really good. And we do synthetic division. Maybe we factor. Whatever our jam is, all I'm looking for is zeros. There's no other context to it. I just want to know where it hits the x-axis. And in that case, specifically, I already have it mapped out for us. Well, they have it mapped out for us. I just wrote it again. If I'm asking where this function is greater than 0, I start by finding where all of my zeros are, because that's the dividing line between greater and less than 0. The things that are greater than 0 are positives. The things that are less than 0 are negatives. The things that are greater than 0 are positives, are negatives, are negatives. Okay? So when I ask, where is this thing greater than 0? Well, it happens anywhere it's positive. So I'll use my unions, negative infinity to negative 4, union, and negative 2 to 2. Okay? So specifically, here and here. If I ask where it's less than 0, I have to be a little more careful this time. See, now it's less than 0 where it's negative. Negative 4 to negative 2, union. Now you would say, well, they're both negative. So can I just say 2 to infinity? You know what, that would actually be a good thing to write on here, my number line. Why don't I just put plus or minus infinity on there? I would say, why can't I just go from 2 to infinity? Well, look at the graph. I want to know when it's specifically less than 0. So it's less than 0, but then it's equal to 0. So I almost need a hole there to exclude this point, because at 5 it equals 0. So I need a double union. We're going to go from 2 to 5, can't touch this, and then get 5 out of there. Say 5 to infinity. Okay. Likewise, when I say something is less than or equal to 0, because this equals, now I'm allowed to include that entire stretch. So now I'll say negative 4 to negative 2, union 2 to infinity. Yes, I know, but it says or equal to. On these ones, I use parentheses because it does not equal. Here it does equal. So these all need to change to brackets. Oh wait, that one's still a parenthesis. Can't touch infinity, right? Unless you're on acid or talking about nirvana. This one, when I say greater than or equal to 0, again, I'm going to have to keep in mind that it equals 0 here, so that's going to factor into my unions here. Greater than, from negative infinity to negative 4, it equals at negative 4, bracket. From, bracket, negative 2 to 2, bracket, union. Do you remember, all the way back when we did our interval notation in chapter 1, how do I say just 5? Right? You don't say 5 to 5 because that's not an interval, it's a single location. So I'm just going to say union 5. Okay? So this idea is that I solve nonlinear inequalities by setting them unequal to 0, find the zeros, because that's a dividing line between greater and lesser, and then just watch out for my brackets and parentheses and all that kind of stuff. Now up here I wrote it like they have in the notes. But what I actually like to do for those is write it more like this, where I'll have dot -4, dot -2, dot 2, dot 5, and you'll see why when we get to the rational functions. And then I actually write my plus, minus, minus like this, so it physically mimics this without having to graph it. See, I could just look at my calculator to do that, or if I have the polynomial, put it into y1. Well, yeah, that's in my calculator. I can go to my table and I can test in between there. I could have put in -5, -3, 0, 3, and 10, and then just look at are they positive or negative. So on to example 1. So this is just the how and the why. Now we put it into action. Okay. Where's my little selecto tool? Okay, it just says solve it. It doesn't say you have to graph it, but I put the graph on there for a reason. A, you better know how to graph a quadratic. You're in pre-calc. But B, it might actually help us when we solve these. See, all of these were something unequal to 0. So first thing I should do is move him over. Got x squared minus 6x minus 27 greater than 0. See, what that does is it takes my parabola like this. And I was asking, where is it greater than -3? Where is it above this line? So all I did by adding 3 to this side is I shifted the goalposts. I took that line and I moved it up to the x-axis and the parabola along with it. Because now I move this -3 line up to the x-axis. The x-axis is where I have zeros, and I know how to find zeros because I've been solving them forever. So, factor x minus 9, x plus 3. So x will equal 9 and -3. So these are my points right here and here are going to be at -3 and 9. Now the reason that I have that graph over to the side is because if I were to actually graph this, well, why would I need to test it if why would I need to test the regions when I can just physically look at it and see that before -3 and after 9 it is above the x-axis? Okay, so sometimes you can just get away with graphing it, but in this case it is greater than 0 from -infinity to -3 parenthesis because it is not equal to, it is just greater than, union 9 to infinity. So, pause it. You do the same thing, and it's these two. Starting with baby steps, just quadratics. Okay, everything to one side of the bus. Minus 14, 0. Factor. And say, oh, also, use your properties. This is a positive parabola. It's going to be like that. And now I know that I'll have zeros at -7 and +2. Set those equal to 0. So if I'm asking where it's less than 0, well, it's everywhere down below that, because if those are zeros, then that is where my x-axis is. So everything from -7 to 2. Over here, different color, here I am. I'm not going to put everything on one side of the bus because this is a perfect square trinomial that has been written as a binomial squared. I can just square root and say x minus 4 pseudo equals, we know it's going to be right, plus or minus 2. So then do y'all remember how to solve these inequalities? When I say this is greater than 2, I can't also say greater than negative 2. It's kind of that whole light side, dark side, absolute value thing, where I'm going to have x minus 4 is greater than 2, but it's less than negative 2. Y'all remember that from, like, what, Algebra 1, beginning of Algebra 2, maybe? So x is less than 2, x is greater than 6. Now that's one way to do it. If I had actually expanded that out, I'd have x squared minus 8x plus 16 greater than 4, subtract the 4, plus 12 greater than 0. Factors of 12 that add up to negative 8 are x minus 2, x minus 6. And again, I see I have a positive parabola with zeros at 2 and 6. This is asking where it's greater than. Well, before 2 and after 6, which is exactly what we had this way. So you can bring back some of those old algebraic concepts. Either way, negative infinity to 2, union 6 to infinity. And again, watch your inequalities as to whether those are going to be parentheses or brackets. So, example, nope, not 4. Not yet, wrong one. On to example 2, there we go. Says, using end behavior. So, A, this one's easier. So I figure I'm going to, we're going to give you a little taste of that split term factor by grouping. Right now, if I just cut this in the middle or if I rearranged it, I'm not going to have a binomial in common when I try to factor by grouping. I have to split one of these middle terms to make it work. Now, again, you'll do it up in Calc 1, Calc 2, maybe. But the process is, there's a whole algorithm for it, but I've always just done it with mental math, guess and check. I'm going to break this negative 13 into a negative 7x and a negative 6x. And again, that was just guessing and checking some numbers in my head. I don't really have a better way to explain it. That is all fuzzy on the left. Come on, you. That's still a little fuzzy, but whatever. Now, do you see how if I cut it right here and factor by grouping, if I take an x out, I'm left with 3x squared minus 4x minus 7, which is a factorable quadratic. Over here, if I take out a negative 6x, I'm left with x plus 1. Here, that factors into 3x and x. I have to have that because that's the only way I'm going to get 3x squared. Factors of negative 7, or you could do the full AC method on it. I'm just going to keep making that disclaimer. We're going to have a minus 7 here and a plus 1 here, because that will give me positive 3, negative 7 makes negative 4. Minus 6x x plus 1, and they share an x plus 1. So when I take x plus 1 out and distribute this back in, we'll have 3x squared minus 7x, and, oh wait, I wasn't supposed to take an x out of here, minus 6, which is again factorable. X plus 1, 3x, x, factors of negative 6, that will get me a negative 7 in the middle, are going to be negative 3, positive 2. So I get x is negative 1, negative 2/3, positive 3. Again, that's one way. The other way would be to take your polynomial here, jam it into synthetic and feel lucky. I've got 3, negative 4, negative 13, negative 6. And I'll feel really lucky about negative 1. Come on, you. 3, negative 1, negative 7, 7, negative 6, positive 6, done. And I'll feel really lucky about a 3. And then I'll feel really lucky about a negative 2/3. And then remember to divide that down because it was actually 3x plus 2, not x plus 2/3. So no matter what, we've got our x-intercepts. We've got our zeros. The title of the problem says, using end behavior. See, from negative infinity to infinity on my x-axis. Oh, got to move that over. I know that I'm going to have an x-intercept at negative 1, an x-intercept at negative 2/3, not to scale, and an x-intercept at 3. Now, why would I use end behavior? Go back to that good old leading term test. It's positive cubic. Positive cubics start at negative infinity, do stuff, and then go up to positive infinity. So that tells me I will start negative, and since it's x-intercept, go through the axis. So now it's positive. X-intercept, go through the x-axis. Now it's negative. X-intercept, go through the axis up to positive infinity. Now it's positive. The multiplicity of these zeros will also affect it. Say 3 happened twice. I would know it goes down through, so I'm in negative town. And then if it happened twice, it would have to bounce off like a parabola. So all that stuff that we did before about quick sketches, and then we would find the extrema in between, now I just don't care. I don't need the extrema, because the whole goal is just to find out where it's less than or equal to 0, which is right here at negative infinity to negative 1. It says or equal to, so we'll put a bracket right here. Union, in between these two, brackets, negative 2/3 to 3. Okay, so whether you want to factor or do this, you don't need all this work. Like, you could have just had that. Okay? So, 1 quadratic and 1 cubic. Give more. Here, 2x squared, subtract, negative 12x, add, plus 16. Now, I'm going to factor out a 2. X squared minus 6x plus 8. and then factor the quadratic. I could have divided by 2. So what's going to happen here is I'll see a parabola where if I had this factored into this, I'll have a x-intercept at 2 and x-intercept at 4, and it'll look like this. Versus if I had divided by 2 and only saw this quadratic, I would still have those x-intercepts. It would just be half as tall. The answer is going to remain the same. I want to know, where is this thing less than or equal to 0? And it's in between those two x-intercepts of 4 and 2. So from 2 to 4. It does say or equal to, so we'll use brackets. For my next guy, again, it is factorable. I'll show you that because I know you know how to do the synthetic version. You just see what you feel lucky about. But we're going to break that negative 12x into 3x and negative 15x. See, 3 and negative 15 does make negative 12, so that's fine. This looks fuzzy again. Or maybe I'm just going cross-eyed after the last few days. That's a little better, but now it's fuzzy on this side. It's going to bother me the whole video. Probably bothers you. If I cut it right there, this side, take out an x and then factor the remaining quadratic. We'll have a 2x and an x. Factors of 3 that will get me to a 7 in the middle are 3, so 2 by 3 is 6, and 1. Over here I'll take out a negative 15, leaving a x plus 3. And sure enough, they have an x plus 3 in common. So all this stuff left, I'll distribute this x back in. 2x squared plus x minus 15, which is again factorable. The only way I'm going to get 2x squared is with 2x and x. Mental math your way around factors of negative 15 to get a positive 1 in the middle. I'm seeing a plus 3 minus 5. And there be my answers, or my x-intercepts, I should say. Negative 3, positive 5 halves, negative 3 again. Okay, that multiplicity is going to come in. If I make a just quick sketch number line from negative infinity to infinity, I have an x-intercept at negative 3. I have an x-intercept at 5 halves. It's a positive cubic, so I know it'll start at negative infinity, it'll end at positive infinity. And because this one happened twice, I know it's going to bounce off like a parabola, happen once, so it'll go through like a line up to positive infinity. So this is going to be negative, negative, positive. You could also just dump it in your calculator and look. Now, what the book wants you to do, this book really likes tables, is they want you to make a table of values in between here and test it by plugging them into the equation. I don't want to do that. I'm lazy. I'm either going to look at my screen or I'm going to use my end behavior that I know how this particular cubic is going to behave. So whether you do factoring, I'm just doing that to show you, you don't have to, or do synthetic. Either way, negative, negative, positive, if I want to know where this thing is greater than or equal to 0, that's important. It's greater than 0, 5 halves to infinity, but it's equal to at negative 3. So I have to include that one point. All right. Oh, sorry about that. I was supposed to zoom in on this as I was doing all that, but you get the idea. Okay, on to 3. So in addition to end behavior, sometimes I can use the characteristics of a graph to get these special graphs taken care of. So what I mean by these special graphs, if I try to solve this, no factors of 8 that add up to 5, I'm going to have to go to complete the square or quadratic formula. Unless, let's go all the way back to Algebra 1. Y'all remember how to find the vertex of this thing. X is negative b over 2a, which in this case is negative 5 over 2 by 1 is negative 5 halves. Go find the function of that. 25 fourths minus 25 halves, so 50 halves negative 20 fourths, so negative 25 fourths plus 32 fourths, 7 fourths, I think. Y'all, the next kid's started puking today, so if my mental math is off, whatever. I know it's going to be positive. No brownie point for you. The idea is, I know the parabola is above the x-axis. Okay, that's the whole point of these and them being special. If I'm asking where a parabola is less than 0, and I know that it never hits the x-axis at all and has end behavior moving upward, where is it less than 0? Never. But if I ask where is that same parabola greater than or equal to 0, everywhere. Okay? Same thing here. But in this case, I recognize a perfect square trinomial. This is x minus 5, the quantity squared. Y'all remember transformation form, vertex form? Y is a x minus h squared plus k. This is in that form. What this is a parabola that moves right 5, no up or down, for a vertex, and then upward she goes. So if I'm asking where this parabola is greater than 0, and it hits the x-axis at exactly one point, from negative infinity until that point, and then everywhere from that point beyond. If I ask where this particular parabola is less than or equal to 0, it's never less than, but it's equal to at exactly one spot. So if you know the behavior of the parabolas, or whatever function you're dealing with, sometimes you don't have to test anything, you don't have to solve anything, you just know. It does. So pause and see what it does. Go back? Yeah, okay. The same thing's going to happen where if I try to solve these, I end up with imaginary solutions, meaning there are no real solutions, meaning it never hits the x-axis. It's a positive parabola that never hits the x-axis. So 3a, 3b, that's a parabola that's floating somewhere up above And if they ask me where it's greater than 0, I'm going to have to say, where. Where is that less than or equal to 0? Nowhere. 3C3D, I'm going to have to move that 16 first. Getting x squared minus 2x plus 1, which is x minus 1, the quantity squared. Which, again, is a parabola that hits exactly once with a vertex right 1. So where is that less than or equal to 0? It's equal to 0 at exactly 1. Where is it greater than 0? Well, everywhere except 1. Negative infinity to 1, can't touch us, and 1 to infinity. There you go. Oh, randomly, I had to double check one of my videos. I know that I'm talking a little quieter here. I got, here. Okay. So, that's my microphone right now. And, I've got a unconscious wife behind me, and I've got 2 goblins on the other side of the wall there. I'm trying to be, trying to be quiet. So if you gotta crank up the volume, I'm sorry about that. It's just what we gotta deal with. Alright, oh, now I gotta fix my camera here. I went and monkeyed with things. Okay, on to example 4. Oh, our got it page here, our thumbs. At this point, I'm going to assume that either you know what you're doing and you don't need any of this, or you do need some of this and you are self-aware and intrinsically motivated enough to try 1 or 2 of these, take a picture of it, send it to me, and say, did I do it right? If you do that, I will answer. Okay? Even today, I answered a couple of kids who had questions. It's just I have to not be beset upon by goblins when I do that. So, or on the floor of a bathroom with goblins. So, again, do the thumbs pages if you need to. Pick one that looks nasty, do it. Otherwise, I'm moving to example 4. So now instead of a polynomial, we have rational functions. And there we go, side quest. In a rational function, again, I'm looking where is something going to be greater than or equal to 0, so I'm always going to set it unequal to 0. Now we know that we can cross from positive to negative at x-intercepts. I can cross from positive to negative at x-intercepts. But how do I go from negative to positive if there's no x-intercept in between? Well, rational functions have another feature, asymptotes. How many times have we seen something like this? Okay, where it'll switch from negative to positive at an asymptote, but it will also switch from positive to negative at x-intercepts. So that means when I'm making my little number line to test, I'm going to have like x-intercepts, asymptotes, x-intercepts, asymptotes. I'm going to have to test at both x-intercepts and asymptotes. Good thing that when we do our rational functions, if you remember, my numerator function and my denominator function respectively get me my vertical asymptotes and my x-intercepts. So all the stuff that we were doing in 2.5 is just going to come back to us. Take this thing, put it together using common denominators, and then find your x-intercepts and your asymptotes. So I need to get common denominators. X plus 1 is missing here. X minus 6 is missing here. Okay, so I'll have 4x plus 4 plus 2x minus 12 all over x minus 6 times x plus 1 is greater than 0. So I'll combine all my like terms and get 6x minus 8 all over x squared minus 5x minus 6. Oh, greater than 0. So common denominators, combine like terms, distribute, all that kind of stuff. And now treat this like when we were graphing, because the idea behind this is to find my little cheater number line here from negative infinity to infinity. Where are those intercepts and asymptotes in between? Here, well, I already know how that factors, right? I know I'm going to have vertical asymptotes at x is 6 and x is negative 1. If I set my numerator equal to 0 and solve, add 8, divide by 6, x is 4/3 is going to be a x-intercept. So I throw these three things on my number line. At negative 1, oh wait, at negative 1 is an asymptote. At positive 4/3 is an x-intercept, and at 6 is an asymptote. Now I can also just kind of sketch my graph for this. Do you see that you're going to have a, where's my other color here? If I plug in 0, I'll have a y-intercept of 4/3 as well. That I'll have degree of numerator is less than degree of denominator. I'll have a horizontal asymptote at y equals 0. So if I were to just quick sketch this, in between negative 1 and 4/3 is my y-axis. I know that I'm going to have a y-intercept at positive 4/3, horizontal asymptote, and I see where it's going to do one of these numbers. Okay, now I could just know that behavior because I know rational functions well enough, or I get my number line, negative infinity, negative 1, 4/3, 6, infinity, and I can either just look at my calculator screen, or I can plug this original function into y1 and just start testing numbers like negative 3, 0, 4, 10 to see if they're positive or negative. And I'll see that they are negative, positive, negative, positive, like this. So either sketch the behavior or just look at your screen. I don't care which, and I'm not really going to be able to tell which one unless I'm specifically requiring it, and I don't do that. Where's that thing greater than 0? Right here, from -1 to 4/3, and again back here from 6 to infinity. I also want you to be very careful as to whether this is greater than versus greater than or equal to, because if it's greater than or equal to, you'd say, okay, I just switched to brackets. One of them's an asymptote, one of them's an x-intercept. So I would need a bracket on the 4/3 and a parenthesis on -1 because I can't touch the asymptote. That's why when I make my number line, I put a dot for an x-intercept and a little dashed line for a asymptote. Just so I remember that when it's or equal to. So if you would, pause it, give it a whirl. Alright. I'm going to move that 1 over, get x plus 6 over 4x minus 3 minus 1 greater than or equal to 0. I'm going to need to turn that into plus a -1 over some denominator. That denominator is going to have to be a 4x minus 3 so that I have common denominators and I can combine stuff. So we'll have x plus 6 minus 4x plus 3 all over 4x minus 3 greater than 0. Combine like terms, clean it up a little bit. Negative 3x plus 9 over 4x minus 3 greater than 0. Look for your x-intercepts and your asymptotes. -infinity to infinity. Vertical asymptote at 3/4. And what's the other one going to be? Positive 3. So asymptote at 3/4. Set my numerator equal to 0. Subtract 9, divide by 3. Get x-intercept at 3. Now I could know my behavior, or I'll bring it up so you can see. Okay, got it. I had to go poke stuff. So here's what I mean, is I can know what the behavior looks like. Okay, if I can quick sketch my graph, just like with my end behavior on the polynomials, I don't need to do anything with the calculator. But look at how easy it is to just take a peek at my calculator and say, until my asymptote, it's going to be negative. From my asymptote to the x-intercept, it's going to be positive, and then crosses at 3, heads down, going to be negative. Okay? Or I can also set this over to ask, and I can just test values in here. Something between -infinity and 3/4, I'll test 0. Oh, hey, look, it's negative. Something between 3/4 and 3, I'll say 2. Oh, hey, look, it's positive. Something after that, like 12. Oh, hey, look, it's negative. So 3 options to run the test. But the goal is get your x-intercepts and your vertical asymptotes. Sketch out a little number line, and then test those areas by knowing what the graph looks like, seeing what the graph looks like, or testing in those intervals. Okay, so however you're going to do it. And this is, where is it greater than 0? To me, that looks like from 3/4 to 3. All right. again. I will subtract 3. X squared minus x minus 11 over x minus 2 minus 3. Going to be less than or equal to 0. I am in need of an x minus 2 upstairs, downstairs to get my common denominators. I'll have a negative 3 times that stuff, getting me x squared. Negative x minus 3x is minus 4x. Negative 11 plus 6 is minus 5, all over x minus 2. So, my number line from negative infinity to infinity. Why is there a hole right there? Oh, because I've been writing on top of a knot in my desk work here. Factor this. Turn that into x minus 5x plus 1. So I know I'll have x-intercepts at 5, negative 1, and I know I'll have a vertical asymptote at 2. Again, I can know what's going to happen here. So remember, if I put a y-axis here, I know that I'll have a positive 5/2, put in a 0 for x, y-intercept. I know I'll have an oblique asymptote that goes through this. I didn't mean to actually mark there. But because I know that it's positive right here, and there's a asymptote, there's an x-intercept, well, it doesn't go down below the axis here. It must have kept going up. That means it's going to start at negative, skirt up through here, up the asymptote, start back down here, negative, come up through this x-intercept, positive. If I know that it does that, great. Otherwise, I'm going to put those numbers into my calculator and I'm going to test the intervals. Or just look at the screen. Either way, where is that less than or equal to 0? From negative infinity to negative 1. Again, from 2 to 5. The question is parentheses or brackets. At an x-intercept, I can have brackets. At an asymptote, I can't. At a x-intercept, I can have brackets. At infinity, I can't. And one more time. Everyone on one side of the bus will have 1 over x minus 1 over x plus 5 greater than or, nope, just greater than 0. I'll add the opposite just to keep that the same. Common denominators. Distribute up top. Combine like terms. This will be x minus x plus 5. Well, that's just 5 over x squared plus 5x. But I'll leave it like this since I know what I have to do with it. Almost there. We are going to have vertical asymptotes at negative 5 and at 0 with no x-intercepts to speak of. Because 5 can't equal 0. Well, wait a second. No x-intercepts to speak of. What does that look like? Remember, degree of numerator is smaller than degree of denominator. So that means I have a horizontal asymptote at 0, and there's no cross through it because there's no x-intercepts. So, tired. It's going to be positive back here, negative here, positive there. Also something that I haven't been able to really point out in class. You see how these just kind of stop? And we know that that goes up forever. But because it's so sharp and close to that asymptote, and it's not supposed to show the asymptote, it's going to stop showing the actual graph. Be smarter than the graph. Okay? Don't just assume it actually quits there. Be smarter. And then, where is this thing greater than 0? Well, from negative infinity to negative 5, union 0 to infinity. Whew. And then, the last part. Blah, 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 do what you just did, except now it's words. I'm going to start yawning more because I'm really tired. So, let's make this a little bit bigger. A group of high school students renting a bus for $600. Oh, God, I remember this problem. Okay, so it's poorly worded. They're renting a bus for $600. They're splitting the cost. Doesn't actually say that in the problem. To take to an amusement park the day after prom. Which, by the way, awesome. But if you're this tired, going and riding a bunch of roller coasters is probably not the best idea. The tickets to the amusement park are $60 less 50-cent group discount per person in the group, meaning your ticket starts at $60, but if there's one more person in the group, now it's $59.50. One more person in the group, $59, $58.50, $58, $57.50. So it's going to keep getting cheaper to get the ticket for every person that you have. And if you're splitting the bus, for every person you have, the bus gets cheaper as well. Write and solve the inequality that can be used to determine how many students go on the trip for the total cost to be less than $40 per student. Why they say less and not less than or equal to, I don't know. Like that one kid didn't have 2 20s in his pocket. He had exactly 99 cents. I don't know. But if they're renting a bus for $600 and it's split amongst all the kids there, can you write that as an expression? $600 divided by how many kids there are. So this is every kid's share of paying the bus. They're also going to have to pay for their ticket. Their ticket is going to be $60 minus a 50-cent group discount per kid. So their share of the bus, their individual ticket to get in, and I want that cost to be less than $40. Write and solve the inequality. So now let's just do the same stuff we were doing, right? I'm going to get common denominators by taking this times x over x. Get 600 plus 60x minus 50-cent x squared all over x is less than, oh, I wanted to bring him over. I can do it now though. If I subtract 40 over minus 40, well, I'll also need to have x's to get my common denominator. Just realized my head's like off the camera there. Like this. So there we go, fixed. Now get common combined like terms. Negative 50 cent x squared, 60x's minus 40x's minus 20x's plus 20x's plus 600 all over x less than 0. And I just realized I wrote all of that behind this cute little window here. Jeez. Get your x-intercepts and your vertical asymptotes. Your vertical asymptote is going to be at 0. I know that much. But I have to solve my numerator as a quadratic to get my x-intercepts. Well, if I have all that equal to 0, I can multiply both sides by 2. 0 times 2 is still 0. I'm going to get x squared plus 40x plus 1200 equal to 0. Ooh, can tell the sleep deprivation is really starting to catch up here. X plus 20, quantity squared. If I subtract that, negative 1200. Half of 40 is 20, and 20 squared is 400, plus 400 is negative 800. This thing doesn't have any real answers. Huh. Well, if I don't have any real answers for my numerator, then that means it has no x-intercepts. If it has no x-intercepts, then I don't have to put anything else on the line. I just need to stop blathering and get my calculator out because I am too tired to mental math this. Okay, so here. I'm actually going to come all the way back here. And I'm going to show you the easier way to do this. Y equals, clear. I've got 600 over x. Adding in their cost for the ticket is 60 bucks minus 50 cents per kid. I'll just subtract that 40 over. Right there in line with it. And then graphify. I see nothing. Because remember, the idea behind this is X is the number of kids that are splitting this bus. It means I got more than 10 kids. It also means I'm going to end up with this many kids, this is total cost. I'm betting the total cost is still going to be more than $10. My window needs to be bigger. I'm just going to ballpark this and say from 0 kids to how many would fit on a bus. Been a long time since I've been on a bus. You know how they always have that capacity sign in the front? I'm betting you're not going to cram 100 high school kids on a bus. Maybe you'll go 70. And my cost per person, let's just assume, well, I know there's more than 10 kids, so 60 bucks, 55 bucks, we'll go up to 120, just to be safe. Now can I see my graph? Oh, yeah, there we go. You see where it goes and hits that x-axis? I want to know where this thing is going to be less than or equal to 0. So I'm going to make this down to -5 just so I can have a sign change, and I will calculate where did that happen. My 0 appears to have happened somewhere between there and 70. Come on, you. Come on, you. There we go. At 60. So I screwed up something back here, but I'm tired and deal with it. At exactly 60. 60 kids tells me I'm exactly at $40. Because remember, I moved my line from 40 down to 0 so that I could find my zeros. Careful. How many kids have to go on this trip for the cost to be less than 40? I just found out, come on you, when it's exactly 40. 60 kids, $40. I need to split this one more kid. 61 kids will get me a cost less than $40 because that one kid just could not find a penny. So, 5. Same deal. Can you write out a polynomial? Well, in this case, a rational function. I don't know if I can anymore because I'm tired. Go ahead and pause and see if you can do better than me. God, I hope you can do better than me. My eyes are swimming. I need to go to bed. Design a fence that's going to enclose a rectangular garden. As soon as I hear rectangular garden, when in doubt, draw it out. Perimeter of 250 feet. Okay, I know perimeter is 2 times length plus 2 times width, and that's going to be 250. The area of the garden has to be at least 1,000 square feet. Okay, well, I know area is length times width, and I know the area needs to be at least, so greater than or equal to length times width, 1,000. Write and solve an inequality to find possible lengths of the fence. We've run across this before. I said it's a very common example of geometric application of polynomials where I get a perimeter and have to put it into area, or surface area and have to put it into volume. I got too many variables. But I can rearrange this to get some variables by themselves. See, if I divide all that by 2, I can rewrite either in terms of L or W, which one I want to replace. Now, if I look at the problem, it says find the possible lengths of the fence. I want L to be there when I'm done, so I'm going to say W is, subtract the L, 125 minus L. So I can replace this and get 1,000 has to be greater than or equal to at least 1,000 feet. I got this in the wrong direction. At least 1,000. I want the area bigger than that. There we go. Length times width. Width is now 125 minus L. I'm just going to go put everything on one side. Say that's negative L squared plus 125L when I distribute. I'll subtract the 1,000, and I want that greater than or equal to 0 now. So I can either solve, not 100% sure if that's factorable, or head back to my handy-dandy calculatron. Y is clear, negative x squared plus 125x minus 1,000 graphophile. Huh. Well, what happened? Could it be that maybe we were missing, well, first of all, I'm like, why are you, God, that screen is just glare and a half right now. Can't even see it. Well, anyway, back here there's a negative answer, right? So I find my 1, 0 over here. I will calculate my 0 somewhere between 0 and 10. 8.59-ish. So I'm going to have a length somewhere around there. I'll just quick double check my window, make sure to 125. Must be way too big. Make sure I don't actually have. Come on, yellow circle of death. Oh, see, we had to check. We had to check. We're going to calculate our other 0 somewhere between 100 and 124. Okay, so we had 2 possible lengths. One was 8 and change, one was 116 and change. Find the possible lengths of the fence. Turns out there was 2. I had to just make my window large enough. But I think y'all know how to solve these. It's just a matter of can you write the problem out. And we have hit the point where I am now rambling incoherently because I'm just that tired. So I got good news for you though. Since you hung in there long enough, see this video is already at 1:12. Since you hung in there long enough, 2-6 is normally a 2-day lesson. This is Thursday and Friday's lesson and assignment. You finished it off. Good job. Your homework will cover all of 2-6, and Friday will be a work day for you to just do whatever you need to because you hung in there with me for an interesting week and a half. So, assignment will be due Monday. Friday will be a work day. I'll see y'all whenever I see you.